Hi, my name is Zhenzi Wang, a PhD student at the Chinese University of Hong Kong. I'm happy to share our work towards exact interaction force control for underactuated quadrupedal systems with orthogonal projection and quadratic programming. Here's the agenda. We show you our motivation, the details of our framework, the verification setup, the results, and the takeaways step by step. Controlling underactuated quadrupedal robots to apply an exact contact force to the environment with a fast reaction, like tracking a desired interaction force command from users, is still open. For example, as shown in the figure below, a robot uses one leg to keep pressing a button. In this case, exact force control is preferred for avoiding the robots falling, since it would otherwise be unstable due to the unmodeled environment. To deal with the contact problem, a method called projected inverse dynamics control is commonly used. Nevertheless, this method cannot achieve an exact contact force control because the force is implicitly manipulated, or it can be achieved by using the motion planner, which loses the fast reactivity of the contact force control. Therefore, we present a novel interaction force control scheme for underactuated quadrupedal systems, relying on the projection method and quadratic programming without requiring force planning. Now let's get into our proposed framework. This figure shows our proposed controller schematic. Our main contributions are highlighted in these three red blocks. Next, we will show you the important details of our framework. Let's recall the projected robot dynamics in the projection method. The standard dynamics equation can be projected into two subspaces by using the orthogonal projection matrix P and the I-P. Based on these two equations, the contact forces can be calculated as follows. To deal with the underactuation problem, this error norm must be minimized. However, a related work shows that it is not directly solvable by an optimization approach. Fortunately, this work provides a way to resolve the underactuation. It decomposes the error norm into the motion space and the constraint space, respectively. The underactuation problem can be then resolved by minimizing these two error norms hierarchically. Note that the tau d is the sum of tau md and tau cd, where tau md is designed for the Cartesian impedance control of the end effectors, and tau cd is extended for the contact force control. Follow the idea of decomposition. We formulate the optimization problem in the motion space by QP, subject to the physical constraints, and then solve the QP problem at the first stage. After the first optimization, the second stage QP optimization problem is formulated in the constraint space, subject to the corresponding physical constraints. One key point we would like to point out is that the active joint selection matrix B in the dynamic equation can be decomposed into two selection matrices Bm plus Bf, where Bm selects the actuators to perform the desired motion tasks, like checking the desired torso pose when standing, and Bf selects the actuators for the desired contact force control. As you can see, we use Bm in the first formula and Bf in the second one to distribute the desired motion and contact force control tasks to the corresponding designated actuators respectively, such that the motion and contact force control tasks can be decoupled to the greatest extent. Finally, the ultimate torque command is composed of the first and second QP problem solutions. To verify our framework, we use the front left leg of the animal C in right scene to exert an side wave and step contact force to the ground, while the other three legs support the torso to track a constant pose. We compare the force tracking performance of our method with the other two methods, HOWSM and PIDC, where the former is short for our method without the selection matrices design, and the latter stands for the projection method for underactuated robots. Here are the results of sine wave force checking. Our method yields the best force checking performance among all the three methods. Besides, by comparing our method with the HOWSM, We conclude that the selection matrices design is the key to decouple the motion and contact force control tasks. And here are the results on step force checking. We can also see that our proposed framework has the best force checking performance with a fast reaction and without requiring a motion planner. So to wrap up, we have some key takeaways. Firstly, we present a novel interaction force control scheme for underactuated quadrupedal systems that does not require motion planning and a force torque sensor. Secondly, for resolving the underactuation problem, we propose a hierarchical QP structure that minimizes the cost functions in motion and constraint space, respectively. Lastly, to reduce the coupling effect between motion and force control, two selection matrices are deployed, allowing us to approach the fast reactive exact force control. That's all. Thank you for your time.